Welcome back to Studious. Today we explore the most abundant, most widely distributed, and arguably most clinically important cartilage type in the entire human body, hyaline cartilage. If you bend your knee right now, hyaline cartilage is silently absorbing the load. When you breathe, hyaline cartilage keeps your trachea open. When you were a developing fetus, hyaline cartilage was the blueprint for your entire skeleton before bone existed. This tissue is everywhere, and understanding it in detail is not just a histology exam requirement. It is fundamental to understanding joint disease, skeletal development, respiratory anatomy, and some of the most common clinical conditions your patients will present with over a lifetime of medical practice. This visual atlas, the Glassy blueprint, is your complete architectural guide to hyaline cartilage. We will move systematically from macroscopic anatomy to molecular networks, covering its 5 primary locations, the developmental blueprint role it plays in the embryo, the perichondrium that keeps it alive, the chondroblast to chondrocyte life cycle of its cells, the ECM engine that gives it its mechanical power, the 3 microzonal matrix rings around each chondrocyte cluster, the articular exception that eliminates the perichondrium entirely, the 4-zone architecture of articular cartilage, the biomechanical gradient across those zones, and finally, the clinical catastrophe of osteoarthritis. Let us begin.
The name hyaline comes directly from the ancient Greek word hyalos, meaning glass, and this etymology is not merely poetic. It is a precise morphological description. When you examine hyaline cartilage under the microscope on a standard H&E section, its matrix has a characteristic smooth, homogeneous, glassy appearance, a pale blue-purple background that looks almost featureless at low magnification, with no visible fiber bundles or structural texture. This glassy appearance is one of the defining histological identification features of hyaline cartilage, and it arises directly from its molecular composition. The type 2 collagen fibers that form its structural scaffold are extremely fine and uniformly distributed, and they share the same refractive index as the surrounding proteoglycan ground substance, making them invisible under standard light microscopy. This optical invisibility of the fibers is what produces the characteristically featureless, glassy matrix. The core traits of hyaline cartilage flow directly from its composition. It is avascular, completely devoid of blood vessels, relying entirely on diffusion through the matrix for its metabolic oxygen and nutrient supply. This avascularity, as we will explore, is both a structural necessity and a clinical vulnerability. It is flexible, capable of deforming under load and recovering elastically, and it is built from specialized cells called chondrocytes, residing within a massive extracellular matrix of protein-sugar complexes and this invisible network of type 2 collagen fibers. Contextually, it sits between elastic cartilage, specialized for flexibility in structures like the ear, and fibrocartilage, the tough, shock-absorbing tissue of intervertebral discs and menisci. Hyaline is the generalist, the most common, most broadly distributed, and most structurally fundamental of the 3.
Hyaline cartilage is not confined to one location in the body. It appears at 5 distinct and anatomically significant sites, each exploiting a specific property of this versatile tissue. Location 1 is the nose. The septal and alar cartilages of the nose are hyaline cartilage, providing the structural framework that shapes the nasal passages and maintains the airway openings, while allowing sufficient flexibility to withstand the minor trauma of everyday life without fracturing. Location 2 is the trachea and bronchi. The C-shaped cartilaginous rings that encircle the trachea and the ring-like cartilage plates of the larger bronchi are hyaline cartilage, providing the rigid structural support that prevents these airways from collapsing during the negative pressure of inhalation. Location 3 is the larynx. Most of the cartilaginous framework of the larynx, including the thyroid cartilage, the cricoid cartilage, and the lower portions of the arytenoid cartilages, is hyaline cartilage, giving the voice box its structural integrity and protecting the vocal folds. Location 4 is the costal cartilages of the ribs, the flexible connective bridges between the bony ribs and the sternum that allow the chest wall to expand with each breath without the ribs shattering under the mechanical stress. Location 5, and clinically the most important, is the articular surfaces of synovial joints and the epiphyseal growth plates of developing long bones. The developmental role of hyaline cartilage is extraordinary. Starting at approximately the third month of fetal development, the entire future skeleton exists as a miniature hyaline cartilage model. This fetal cartilage blueprint is then systematically replaced by bone through endochondral ossification, a process where the cartilage template is invaded by blood vessels and osteoblasts and converted into permanent bone matrix.
One of the most important structural features of hyaline cartilage, and one of the most clinically significant, is its outer envelope, the perichondrium. Because hyaline cartilage is completely avascular, it faces a fundamental survival challenge. How does it receive the oxygen, glucose, and growth factors it needs without any blood vessels penetrating its matrix? The answer is the perichondrium, a dense connective tissue sheath that wraps around the outer surface of hyaline cartilage and serves simultaneously as its structural boundary and its metabolic lifeline. The perichondrium is organized into two distinct layers with completely different functions. The outer layer is the fibrous layer, a tough, mechanically robust layer composed primarily of type 1 collagen fibers and fibroblasts. It provides the structural integrity of the entire cartilage unit, resisting tension and protecting the delicate cartilage beneath from mechanical disruption. Blood vessels, lymphatic vessels, and nerve fibers run through this outer fibrous layer. The inner layer is the chondrogenic layer, the biological nursery of the cartilage. It contains chondroprogenitor cells, the precursors to chondroblasts, which, when activated by mechanical or biochemical signals, can differentiate into chondroblasts and then produce new cartilage matrix. This is the mechanism of appositional growth, the process by which new cartilage is added to the surface of existing cartilage by cell division and matrix secretion at the periphery. The perichondrium's vascular network drives nutrients into the avascular cartilage matrix purely by diffusion, a slow and limited process that explains why cartilage heals so poorly after injury. There is one critical exception to the universal perichondrium rule, a rule breaker that we will examine in detail shortly.
Within hyaline cartilage, two sequential cellular populations are responsible for building and maintaining the tissue throughout life. Understanding their relationship, the transition from active builder to quiet maintainer, is essential for understanding both normal cartilage physiology and the limited capacity for cartilage repair after injury. The first population is chondroblasts, the progenitors, the builders. Chondroblasts originate from the inner chondrogenic layer of the perichondrium and are highly metabolically active cells. Their function is matrix construction. They synthesize and secrete all of the components of the extracellular matrix, type 2 collagen, proteoglycans, hyaluronic acid, and glycosaminoglycans, releasing them into the surrounding space to build the cartilage matrix outward. Chondroblasts are oval-shaped cells with an active, large nucleus and abundant rough endoplasmic reticulum and Golgi apparatus, reflecting their intense secretory activity. As chondroblasts continue secreting matrix, they progressively surround and encase themselves within their own secretions until they become trapped, completely embedded within the dense matrix they have produced. At this point, they have become chondrocytes, the mature, resting residents. Chondrocytes are the long-term cellular inhabitants of hyaline cartilage. They sit within small cavities in the matrix, called lacunae, spaces that perfectly conform to the shape of the cell that occupies them. Chondrocytes have a characteristically rounded shape, with basophilic staining cytoplasm. They are far less metabolically active than chondroblasts, but they are not inactive. They continuously maintain the surrounding ECM components, responding to mechanical loading signals and biochemical cues to remodel the matrix as needed. A key architectural feature, chondrocytes in hyaline cartilage are frequently found in isogenous aggregates, clusters of 2, 4, or more cells sharing proximity, all descended by mitotic division from a single original chondroblast.
The extraordinary mechanical properties of hyaline cartilage, its ability to withstand compression, distribute loads, absorb shock, and recover elastically, are not produced by its cells. They are produced by its extracellular matrix. And the ECM of hyaline cartilage is one of the most elegantly engineered biological materials in existence, with 4 components working in precise molecular concert. Component 1 is type 2 collagen, the primary structural scaffold. Type 2 collagen forms the invisible fibrillar network that gives the matrix its tensile strength and its characteristic glassy appearance. On H&E sections, the overall matrix stains heavily basophilic, blue-purple, because of its rich nucleic acid-binding proteoglycans and hyaluronic acid. Component 2 is proteoglycans, enormous brush-like molecules formed by a central core protein with many gag chains radiating outward. The most important proteoglycan in cartilage is aggrecan, which consists of a core protein with hundreds of chondroitin sulfate and keratin sulfate chains attached. These aggrecan complexes are in turn attached to long hyaluronic acid backbone molecules, forming enormous macromolecular aggregates that are physically trapped within the collagen scaffold. Component 3 is sulfated glycosaminoglycans, particularly chondroitin sulfate and keratin sulfate, which are densely negatively charged. This strong negative electrostatic charge is the engine of the water trap. The negatively charged gag chains attract enormous quantities of positively charged water molecules by electrostatic and osmotic forces, creating immense trapped water pressure within the matrix, a turgor pressure that resists compression. Component 4 is this water itself, comprising up to 80% of the wet weight of articular cartilage. When compressed, this pressurized water distributes the load and allows the matrix to function as a hydraulic shock absorber. Combined with the electrostatic bonds between proteoglycans and collagen fibers, this gives hyaline cartilage its remarkable capacity for repeated compressive loading without permanent deformation.
One of the most sophisticated features of hyaline cartilage histology, and one rarely appreciated by students who focus only on cell identification, is that the extracellular matrix is not uniform throughout the tissue. Instead, it is organized into 3 distinct microzones, arranged in concentric rings around each chondrocyte, or isogenous aggregate, each with a different molecular composition and a different staining intensity, reflecting a different functional role. The innermost ring is the capsular matrix, also called the pericellular matrix. It immediately surrounds each individual lacuna, wrapping tightly around the cell's immediate environment. On histological sections, the capsular matrix stains extremely densely, appearing as a dark ring around each chondrocyte. Its molecular composition is unique. It contains the highest concentration of sulfated proteoglycans in the entire tissue, and it is rich in type 6 collagen, a minor collagen type that plays no significant role elsewhere in the tissue, but is critical here. Type 6 collagen forms a molecular cage that anchors the chondrocyte to its lacuna wall via integrin receptors on the cell surface, physically coupling the cell to the matrix and allowing it to detect and respond to mechanical deformation signals. The middle ring is the territorial matrix, surrounding the entire isogenous aggregate rather than individual cells. It is rich in glycosaminoglycans and contains a network of randomly arranged type 2 collagen fibers. It stains less densely than the capsular matrix, but more densely than the outer zone. The outer field, the interterritorial matrix, is the vast expanse of extracellular matrix found between the various chondrocyte clusters. It is the bulk of the cartilage volume, contains the most type 2 collagen, and is where the majority of compressive load distribution occurs. It stains lightest of the 3 zones on H&E, reflecting its relatively lower proteoglycan concentration compared to the pericellular and territorial zones.
We have established that the perichondrium is the universal lifeline of hyaline cartilage, providing the vascular supply for diffusion, the stem cell reservoir for repair, and the structural outer envelope. The universal rule is that the perichondrium covers the surface of all hyaline cartilage. But there is one critically important exception to this rule, and it is not a minor anatomical footnote. It is a fundamental biological adaptation that defines the most clinically important form of hyaline cartilage in the body, articular cartilage. The hyaline cartilage that covers the opposing bone surfaces inside synovial joints, the articular cartilage of the knee, hip, shoulder, elbow, and every other movable joint, completely lacks a perichondrium. None. Zero. The perichondrium is absent from this surface entirely. The reason is mechanical. The perichondrium is a fibrous connective tissue layer. Inside a synovial joint, the articular surfaces are subjected to massive, repetitive friction and compressive loading every time the joint moves. If a perichondrium were present on the articular surface, the shear forces generated during joint movement would rapidly destroy it. Fibrous tissue cannot withstand that mechanical environment. Instead, articular cartilage has evolved a remarkable adaptation. Without a perichondrium, it is directly bathed in synovial fluid, which provides lubrication and also serves as the diffusion medium for nutrient delivery into the avascular cartilage. But to survive and function under extreme, repetitive mechanical stress without any outer protective envelope, articular cartilage has been engineered into 4 highly specialized biomechanical layers, a zonal architecture of extraordinary sophistication that we will examine in detail in the next slide.
Articular cartilage, lacking a perichondrium and directly exposed to the mechanical demands of joint loading, is organized into 4 sequential biomechanical layers from the joint surface down to the underlying bone. Each layer has a distinct cell morphology, collagen fiber orientation, biochemical composition, and mechanical specialization. Layer 1 is the tangential zone, also called the superficial zone. This is the outermost layer, in direct contact with the synovial fluid and the opposing articular surface. In the tangential zone, chondrocytes are flat and elongated, and their collagen fibers are oriented parallel to the joint surface, tangentially. This parallel fiber orientation is specifically designed to resist the shear forces generated when the 2 joint surfaces slide across each other during movement. The tangential zone also contains the highest collagen content of all 4 layers and is the only zone where chondrocyte proliferation occurs at a meaningful rate. Layer 2 is the transitional zone, the primary bulk of articular cartilage, accounting for 40 to 60% of its total volume. Here, chondrocytes become more spherical and are arranged in lower density. The collagen fibers transition from parallel to a more random oblique arrangement, and proteoglycan concentration increases significantly. Layer 3 is the radial zone, the deep zone, and this is the primary shock absorber of articular cartilage. Chondrocytes here are stacked in strict vertical columns perpendicular to the joint surface, and the collagen fibers are oriented radially, perpendicular to the surface. This perpendicular arrangement maximizes resistance to compressive forces transmitted straight down through the joint. Layer 4 is the calcified zone, the critical interface between cartilage and bone. Here, the matrix is mineralized with calcium salts. Chondrocytes are abnormally large and hypertrophic, and the primary function is structural anchoring, bonding the articular cartilage firmly to the underlying subchondral bone.
The 4 layers of articular cartilage are not simply anatomical zones with arbitrary properties. Together, they constitute a continuous biomechanical gradient, a systematic change in cell shape, force resistance capability, and biochemical composition with increasing depth from the articular surface to the bone interface. This gradient is one of the most sophisticated examples of tissue engineering in human biology. In the tangential zone at the surface, chondrocytes are flat and elongated. The force resistance is specifically directed against shear stress generated by sliding motion, and the biochemical profile shows the highest collagen content of any zone, combined with the lowest proteoglycan concentration. Moving into the transitional zone, chondrocytes become spherical and sparse. The zone acts as a mechanical transition buffer, distributing loads between the shear-resistant surface and the compression-resistant deep zone, and proteoglycan concentration rises significantly. In the radial zone, chondrocytes are arranged in strict vertical columns perpendicular to the surface. The primary force resistance is maximum compressive resistance. This zone bears the greatest compressive loads in the joint, and the biochemical profile shows the largest diameter type 2 collagen fibers in any zone, the highest proteoglycan concentration, but counterintuitively, the lowest water content of the non-calcified zones. Lower water content in the deep zone reflects a denser, more mineralizing environment. In the calcified zone, chondrocytes are abnormally large and primarily focused on anchoring. The matrix composition shifts to calcified hydroxyapatite-bound material, binding directly to subchondral bone. Two critical gradient relationships run across the entire depth of the tissue. As depth increases, water content decreases, and as depth increases, the primary mechanical resistance shifts from shear to compression.
We have now built a complete understanding of normal hyaline articular cartilage architecture. This understanding makes the pathology of osteoarthritis the most common joint disease in the world, affecting over 500 million people globally, immediately comprehensible from first principles. Osteoarthritis begins specifically and consistently in the tangential zone. Panel A, the mechanical failure cascade. The tangential zone, being the outermost layer of articular cartilage and the one in direct contact with the opposing surface, is the zone subjected to the greatest cumulative shear stress across a lifetime of movement. With advancing age, repetitive mechanical loading, obesity, or previous joint injury, the tangential zone gradually degrades. The flat, elongated chondrocytes lose their ability to maintain and renew the dense parallel collagen fiber network that defines this zone. The collagen fibers develop microscopic cracks, the surface loses its smooth, low-friction quality, and eventually the tangential layer begins to physically fragment, breaking off as free cartilage fragments called wear particles that are released directly into the joint capsule. Panel B, the biochemical cascade. These free cartilage fragments are foreign bodies within the synovial joint environment. The local macrophages of the synovial membrane recognize them as damage signals and become activated. Activated macrophages release a cascade of inflammatory mediators, including interleukin-1, tumor necrosis factor, and most critically, matrix metalloproteinases, or MMPs. MMPs are enzymatic proteases that directly cleave and degrade collagen and proteolysis.
We close with the complete synthesis, the blueprint summarized, your comprehensive revision reference for every aspect of hyaline cartilage covered in this video. Locations and origins. Hyaline cartilage is found in the trachea, larynx, nose, costal cartilages of the ribs, articular joint surfaces, and the epiphyseal plates of developing long bones. Its developmental role as the primary fetal template for endochondral ossification means that the entire long bone skeleton passes through a hyaline cartilage phase before becoming permanent bone. Cells and boundaries. The perichondrium is the two-layered vascular lifeline covering all hyaline cartilage except articular surfaces, consisting of an outer fibrous layer providing structural integrity and an inner chondrogenic layer housing progenitor cells. Chondroblasts are the highly active edge-dwelling matrix builders, secreting matrix until they trap themselves and mature into chondrocytes. Chondrocytes are the mature maintainers, living in lacunae and grouped in isogenous aggregates. ECM neighborhoods. The matrix around each chondrocyte cluster is organized into three concentric zones. The capsular matrix, immediately surrounding each lacuna, rich in type 6 collagen and sulfated proteoglycans. The territorial matrix surrounding the entire isogenous aggregate, rich in randomly arranged type 2 collagen and GAGs. And the vast interterritorial matrix between clusters, the bulk structural material of the tissue. The articular exception. Articular cartilage completely lacks a perichondrium, is bathed in synovial fluid, and is engineered into 4 biomechanical sites: tangential, transitional, radial, and calcified, each tuned to a specific mechanical demand. Osteoarthritis begins specifically in the tangential zone, producing cartilage fragments that trigger macrophage activation and MMP-mediated matrix destruction. This is hyaline cartilage, the glassy blueprint of the human body. Thank you for watching Studious.